Now we're finally ready to talk about the RSA Cryptosystem. In the last lesson, you'll remember that we learned about the symmetric key cryptosystem. And so that was a situation where Alice and Bob would have to meet in advance or somehow communicate over a reliably secure channel in order to decide upon that secret key that they both share. And remember what that was. That was the N and the K. They had to know, both of them had to know those two numbers in order to be able to use this simple system that we call the symmetric key cryptosystem. Now the problem with that, as we mentioned before, is that if Eve can possibly find out, intercept the in this example here, the 3322514119, if she can possibly intercept that, who's to say she couldn't have intercepted the communication when they decided upon the N and the K? So that's the downfall of this symmetric key cryptosystem. So RSA is going to fix that. It's going to not have this weakness. So is there a better way that does not involve this prior communication? Yes, and it is called public key cryptography. So in this public key cryptography, Bob, the receiver, is going to have an encryption key that he provides publicly so that anyone can use it to send him an encrypted message. Anyone can see this public key. The sender can see it. Even Eve can see it. Anyone can encrypt any message they want to send to Bob. But only Bob holds that matching decryption key, and he holds that privately, so no one else knows about that. And that's what's great about this. He doesn't have to communicate that to anyone. Only he has to know that private key that's going to unlock a message. So when Eve intercepts this message that Alice has locked up, she can't decrypt it. Only Bob, who holds the private key, can decrypt the message. The most widely used public key cryptography system is called the RSA cryptography system. And it's called that because those letters come from the names of the people who developed it back in 1978. So it was someone by the last name Rivest, and then Shamir, and then Adelman. Those three worked together to come up with this system. And the security of this rests upon the assumption that it's difficult to factor large numbers. And we saw before that we don't have an efficient algorithm to factor any number that's thrown at us. You know, if the numbers are small enough, yeah, we could have a algorithm that could try a bunch of numbers and eventually come up with the right ones. But if we're going to be feeding that algorithm these huge numbers, then we don't have an algorithm yet. It's not been found that can easily factor large numbers. And so that's what the security of this rests upon. So let's go over how this works. How will the public key be prepared and the private key using RSA? So first of all, Bob. Remember, Bob is the receiver. He's going to be receiving the message, and he's going to be broadcasting the public key. So he is going to select two large prime numbers, P and Q. Okay, so very large. Now in our examples that we go over, our numbers aren't going to be that big. But if he wants this to be very secure, he will choose two very large prime numbers. We'll call one P and one Q. Now he's going to compute the product of those two numbers, which is, we'll call N. N will be the product of P and Q. And And he's also going to find something we're going to call phi, which is p minus 1 times q minus 1. So you just subtract 1 from each of those prime numbers, multiply those together to get this number called phi. Now, Bob is also going to find an integer that we'll call e, such that the GCD of e and phi is equal to 1, meaning that e and phi are relatively prime, right? So he has to find a number that's relatively prime along with phi. We'll talk here later about how that's done, how he finds that integer e. Now, here's what he has to do. He has to compute the multiplicative inverse of e mod phi. And that then is going to give him an integer such that e times d mod phi is equal to 1, right? That would be the definition of what the multiplicative inverse of e mod phi is. We have a lot of rhyming going on in these instructions here. Now, the public key, the one that he gives to anyone who wants it, just throws that out to the public, is capital N and E. And N again is that product of P and Q. Now, here's the deal. This N is going to be a big number, and if someone could easily factor any old big number, then they could come up with P and Q, which would be very helpful for them. But that's the idea, is that it's going to be hard for them, for anyone who wants to try to decrypt this, to come up with P and Q. So he just releases the product of P and Q, which is N. And they're not going to be able to efficiently find, anyone else will not be able to find P and Q very easily, especially if it's if P and Q are both large numbers to begin with, then N is going to be very large also. Okay, so he's going to give out N, and he's also going to give out E. Then what he needs is just to know this multiplicative inverse of E mod phi, which is D. And remember, the public can't find that, because they don't know phi. They have not been told phi, so they can't find the multiplicative inverse of E mod phi. Now, once these numbers are determined, N and E and D, then there are some equations that can be used, some formulas that can be used to turn plain text into ciphertext, and then to take ciphertext and turn it back into plain text. Remember, we were using M for plain text and C for ciphertext. Ciphertext is what's been encrypted. So this first box here is going to take plain text, which is the M. It's going to take it to the power of E, and then take all of that mod N. That's going to give anyone the ciphertext to send to Bob. So C is found by that first formula there. Then Bob gets C, and he knows D. He's the only one who knows D. So he's going to take C to the power of D mod N, and that will give him the plain text back. These two formulas are inverses of each other, so whatever we encode is always going to be decoded correctly using this second formula. So here's how the process works. The receiver is going to pick two large prime numbers, P and Q. Then he will take P times Q and get N. Then he'll also find phi, which is P minus 1 times Q minus 1. Now, he has to find an integer E such that E and phi are relatively prime. Now, how is he going to find this E? Well, and how are we going to find it? Well, we would just choose some E, and then check to see if the GCD of E and phi is 1. So since this is going to be a pretty big number, phi is going to be a pretty big number, and E is probably going to be a pretty big number, you'll probably get lucky and choose some E that ends up being relatively prime to phi. But so you're just going to choose something and check, make sure, are they really relatively prime? And if they're not, you know, you can go through that Euclidean's algorithm real quick to find the GCD of the two numbers. And if they don't equal, if the GCD isn't equal to 1, then you just keep guessing, try another E until you find one that works. Now, I don't think in the examples that you're going to do, you're actually going to have to come up with an E. You'll be given problems where you're already told what E has been used. Okay, now that we know E and phi, we're going to find the multiplicative inverse of E mod phi, and we'll call that D. Then the public key for encryption will be the N and the E. That's what everyone can get if they want to correspond with Bob. And then they will find the ciphertext by using this formula. That will convert plain text into ciphertext. And then the private key for decryption that only Bob will know is D. And then he can use this formula to go back to the plain text. And so that will be used to convert the ciphertext into plain text. Okay, so let's go through this, how it looks here. Here's Bob. He's got the private key, and then there's a public key that anyone can find. That public key is the E and the N. And maybe he'll say, okay, I'm using RSA cryptography. E is equal to 859 and N is equal to 1829. Now this is an example with pretty small numbers. You know, he was supposed to find P and Q that were large prime numbers, and P times Q equals N. So to get 1829, he didn't have to have very large numbers for P and Q. So in reality, he would choose bigger numbers P and Q and end up with a much larger N. But for our examples, to make things a little easier, we're going to keep the numbers small. Then he would have computed using the N and the E. He would then have found the private key D, and D would be 79. So let's say that Alice wants to send the plain text message 1211. So she'll use this public key, and so she will do this. She'll take M to the E mod N. And so that's going to be, so M is the 1211, E is 859, and then N is 1829. So the ciphertext is going to be found by 1211 to the 859th power mod 1829. And that, now when you're doing this, you'll want to use a calculator, obviously, so would Alice when she's doing it. Anyway, so she gets 388 as the encoded message. She sends that on over to Bob, and Bob then uses this other one, and he would take the 388 that he received, taken to the power of D, which is 79, and only he knows that D is 79, mod 1829, and then he gets 1211. Now this isn't showing that it going all the way back to letters. Remember, a message usually starts with letters, and then we find the plain text by using that alphabet system that we did last time. So this example here is just going to stick with the numbers and see how we go from plain text to ciphertext back to plain text. So he would get the same plain text that Alice started with, the 1211. Now let's go through an example here. I have over on the top right those instructions that we just went over on how to do this. And you won't have to have this memorized or anything, so you can always refer to this during your assignments and even during the test. Okay, suppose that Alice and Bob are using the RSA Cryptosystem to send a message. Bob's going to select P to be 7 and Q to be 17. Now these definitely aren't large numbers. Remember, they're supposed to be, but again, for our examples, we're keeping the numbers small. First question, what is the value of n? So he already knows P and Q. He just selected them. And remember, P and Q have to both be prime. So P is 7 is prime, 17 is prime. So that's good. Multiply those two together, right, to get the n. So n is going to equal P times Q, which is 7 times 17, which is 119. Now, what is the value of phi? Now, notice this symbol that I have circled here doesn't really completely match up with what's in that box at the top, right top. Phi looks a little bit different. Now, the book, I think, shows the phi like what's in this box to the right. But when we're typing things out in Word or PowerPoint, or even just writing them out, it's easier just to put the circle with the line through, and that also means phi. So when you see that circle with the line through, that's referring to that same value as you see with that little bit different of a symbol up there in the top right box. Okay, so what is the value of phi? Remember that phi is, subtract 1 from the P and the Q each. So we're going to have a 6 and a 16. Multiply those together, we get the phi. Now, if E is chosen to be if E is chosen to be 19, what is D? Okay, so remember, we just choose an E. That E better be relatively prime with phi, and we'll find out here soon. But and then eventually we want to find D. So what is D? D is that multiplicative inverse of E mod phi. Okay, so we'll start out with this remembering that E is 19 and phi is 96. So we'll start out with this process, Euclidean's algorithm, to help us find the multiplicative inverse of 19 mod 96. So remember, we start out with the two numbers written on the left with the largest one first. Doesn't matter which one was E and which one was phi, you're always going to put the largest one first. And then we go through our process. First number that we get is 96 mod 19. It's equal to 1. So then we go one more step, 19 mod 1, and we get 0. So then we'll step back and say, yes, our GCD was in fact the one right before the 0, which is the 1. So we know that that's the GCD of E and phi. And remember, we can't find the multiplicative inverse of two numbers unless their GCD is equal to 1, unless they're relatively prime. So part of this process is verifying that, yeah, the GCD is 1, and we've got it here, okay? But remember, there's more to finding this multiplicative inverse. We have to then find this linear combination. We have to go and find how the GCD can be written as a linear combination of those two original numbers, right? That's what we've done in the past. So we remember that formula. So we would say that 1 is equal to, and we use the two numbers in front of the 1, which is the 96 and 19. It would be that pattern that you've remembered, 96 minus 96 div 19 times 19. And we're going to keep the 96 and the 19 there, but we do want to evaluate that div. So the div, 96 div 19 ends up being 5. So we're going to have 1 equals 96 minus 5 times 19. Remember, we're trying to write the 1 as a linear combination of those original numbers. So what are those actual numbers, the s and the t part, that we called them s and t, at one point, right? What comes in front of the 96 and what comes in front of the 19? Well, we can tell by what we just came up with. We would have a 1 in front of the 96, right? And a -5 in front of the 19. Okay, so we've just written that as a linear combination of the 96 and 19. Now, here's where we need to be careful. Originally, when we were talking about finding this linear combination, we called the first number s and the next number t. Now, here, though, s is important because remember, we're going to find that multiplicative inverse by taking what we called back in that earlier lesson, S mod n, right? S mod n. So the key to finding this multiplicative inverse is knowing what's S and what's the mod n. Okay, so here's just a general way to always make sure you know which of these numbers is S. It's not necessarily going to be the first one, which would be a 1. It's between the 1 and the -5. Which of those is going to be what we use as S when we take S mod n to find the to find that multiplicative inverse? Well, the one that's in front of E, not phi, but the one that's in front of E is our S that we want to use. So look back up here at the top. We said that E is 19. So the one in front of 19 is our S. So our S is going to be a -5. So D, which is that multiplicative inverse, is going to be S mod n. And mod n was referring to the fact that we were using mod n, that we were finding the multiplicative inverse of something mod n. So the mod one's always going to be phi. Phi is always going to go, whatever phi is here, that's going to go right there. So we take the number in front of E and put that there, and then mod phi, put that there, and then find the answer, and we get 91. So for this problem, we've found D. D is equal to 91. Now this is the same problem, and so far we've found that we know that n is equal to 119, phi is equal to 96, and if E was chosen to be 19, we found that D is equal to 91. So if Bob receives ciphertext C equals 23, and again, we're keeping our plain text and ciphertexts really small, and they're not corresponding to letters, just because we're just concentrating in this section on plain text to ciphertext and back. But there would be a scheme, maybe like that alphabet scheme that we talked about before, to actually take plain text and put it into letters, if that's what the goal was. Maybe it is numbers that are being sent, and that's all that we need. But anyway, don't worry about it that we're not going all the way back to letters in these examples. We're just kind of simplifying the process a little bit so that we don't have that extra step to worry about. Okay, so if Bob receives ciphertext C equals 23, then what was Alice's plain text M? Okay, so we're going to use that that second formula over there on the right. We're going to, the ciphertext is C, that's a 23. So we'll put 23 in for C, and we take 23 to the power of D. D is 91. So 23 to the 91st power mod 119, and 119 is the n, right? So that's where we get the 119. Okay, so we end up with 107. And so that would be Alice's plain text message. But now let's go back further. What if the plain text message started out as 12? What would the ciphertext have been? So C is equal to 12 to the power of E. E is 19, so 12 to the 19th power mod 119. Again, it's n. We take mod n. And we could put that in your calculator and get a 96. So that would be the answer there. So as long as we know N and E and D, then we can go back and forth like this. Now remember, the public can always go from plain text to ciphertext because they know, looking at this first box here, the first blue box, they know everything they need in order to come to this, get the ciphertext. They know M, which is the plain text. They know E because that's part of the public key. They know N because that's part of the public key. So anybody can change to ciphertext, but only those people who know D, which is then used in that second blue box, can go from ciphertext back to plain text. Let's go through another example. Now, if you'd like, I think it would be good if you could maybe, if you think you're maybe following this and know what to do, you might want to pause the video right here and try to get all of the answers to this problem here on your own, and then you can run the video and see if your answers match up to mine. So you might want to do that, or go back to the notes later, cover up all the answers and just try this again and try it on your own. So we have Alice and Bob using the same system, and Bob is selecting P equals 17, Q equals 11. So what's the value of N? It's we multiply P and Q together, so we get 187. Phi is going to be, so we subtract 1 from the P and the Q, multiply those together and get 160. Now if E is chosen to be 3, what is D? So remember that what we want to do is we're finding D by getting the multiplicative inverse of E mod phi. Remember that. And so E is equal to 3, phi is equal to 160. So we need to get the go through Euclid's algorithm for these two numbers. Remember, the largest one we start with first, so we have 160 and then a 3. And then we're going to take 160 mod 3, we get a 1. Then go one more step, 3 mod 1, we get 0. So once we get 0, we step 1 back, and then that is our GCD, and that's a 1. It should always be a 1 if we chose if we chose E correctly, right? Because E needs to be relatively prime with phi. So we should always end up with a 1 there if we chose E correct, if E really is relatively prime with phi. Okay, so now that we have this, let's try to, in order to find that multiplicative inverse, we need to write 1 as a linear combination of the two numbers 160 and 3. So we'll use that little pattern where we can write 1 as a linear combination of those two previous numbers, which is 160 and 3. So it'll be 160 equals 160 div 3 times 3. And then evaluate that div, and we have a negative 53 for that. Now, this was a very short example, and they aren't always this short, but we like it when they are, because we don't have to do any substitution. We've got our linear combination of the original numbers just after this one equation, right? 1 is equal to something times 160 plus something else times 3. And let's kind of write it so that we can see clearly what those two numbers are in front of those two original numbers, 160 and 3. So we can write it this way, and we see that we have a 1 in front of the 160 and a negative 53 in front of the 3. Now we need to find which one is our S that we're going to use to find D, right? So remember, we've got the 160 and the 3. We ask ourselves, which one is E? E is the 3, and it's the number in front of the 3 that we want to use for our S, okay? So it would be that negative 53 that we're going to pull out and take that number mod phi. So D is equal to the negative 53 mod phi, which is mod 160, and we get 107. So D is equal to 107. So what would be the public key that's given out? It'd be the N and the E. And then what's the private key? That would be the value of D, which is 107. Okay, so there's one more thing I'd like to talk about, and that is this challenge activity that's in this section. It says the following parameters are chosen to generate the public and private keys for the RSA Cryptosystem. They give us a P, they give us a Q, and they give us an E. Then they say determine which of the following numbers is the correct choice for the private key D. Now, you can go through the whole process, and maybe you want to get some good practice. Okay, so maybe I shouldn't even be telling you this, because maybe I should be encouraging you to go through the whole process, come up with the D. But there are a lot of these questions, and just to keep you from having to go through this process every single time, I just wanted to point out something. Remember that D is that number for which, if it's really the multiplicative inverse of E mod phi, which is what it is, then E, look down here at this equation at the very bottom right, E times D mod phi would end up equaling 1. That would be what the multiplicative inverse of E mod phi is. It's what number times E taken mod phi gives us 1. So when you're given a choice of these possible values for D, you could just go through the whole process to come up with your D, or you can check to see which of those numbers satisfies the E times D mod phi equals 1. So that might be, since it looks like they're going to be having you do this a lot of times, you can kind of take that shortcut. That doesn't mean that you're going to not have to do this long process, because there's other questions where it says, what is the answer to D and for D, and then you have to go through the whole process. But when they're giving you options like this, the shortcut is just to take that number as D, if it's really D, multiply it by E, take mod phi, and see if you get 1. And if you do, then that's the correct D. If you get something besides 1, then you know that's not the correct D. Now, this is one of the times where I'm going to give you some extra practice. You can always rework the problems I just showed you. You'll also be able to rework some problems maybe that that the book talks about, that Zybooks talks about. But you can also go through this one extra additional exercise. So you have the participation and challenge activities for this week, but there's always at the end of Zybooks there's the additional exercises, and I don't always, I haven't up until now assigned any of those, but this is a good practice one to do. So this is an additional exercise, and called encrypting and decrypting a message with RSA. So it gives you, the different numbers and, kind of talks through it, but it asks for different things like what's N and phi, what's D, what's the ciphertext in a certain case, what's the plain text in a certain case. So this would be good practice along with some of the other examples that you've seen in the book and that we've done here. You really do want to be able to go through that entire process because maybe a question on the test could be, here's all of the different numbers, what is D? So you could have to do that, or at the very least, remember we had a section a while back, which was finding the multiplicative inverse of two numbers mod something. So of one number mod the other number. So on the test, you could very well have a question where you're given some numbers and you're asked to find the multiplicative inverse. So I definitely want you to know how to go through this entire process. So this is just a good extra practice for this section.